unremarkable stones lining creek beds, gravel bars, or road cuts. But in the right location, those bland, river-worn cobbles can hide something extraordinary. High-grade rough gems encased in weathered rind or opaque host rock, indistinguishable at a glance from throwaways. One miss is all it takes to leave serious value behind. Take serpentine cobbles, for instance. They often appear as dusty olive green or grayish lumps, soft-edged and unimpressive. Yet in jade-producing regions like British Columbia or Myanmar, a cobble of this type can contain nephrite of cutting grade, a translucent core worth hundreds per kilo. Without a field cut or tap test, you'd never know. The same goes for rhyolite boulders in opal fields or dark basalt nodules in volcanic pipes. Texture, not color, is the first tell. Seasoned field collectors learn to recognize 3 early flags. First, unexpected heft. When a stone feels denser than it looks, a clue to high SG materials like jadeite or corundum 3.34.0 versus average rock at ~2.6. Second, surface breakage or chipping that exposes waxy or glassy luster underneath. And third, nodular or botryoidal habits, bulbous forms suggesting chalcedony, agate, or other silica-based minerals. These traits often co-occur in gem-rich terrain, but are routinely discarded by the untrained eye. Weathering can obscure nearly all diagnostic features. In desert environments, opalized wood can take on a chalky rind. In tropical zones, lateritic crust can mask the green translucence of jade. Only a controlled break or careful abrasion will show what's beneath. But here's the irony. Many of these stones break too cleanly to catch attention. When a rock snaps without grain, cleavage, or fracture planes, it's often a sign of cryptocrystalline or amorphous structure, a potential win. So why are they so often ignored? Convenience. Casual pickers tend to favor colorful, transparent, or already polished materials. Anything that looks like just a rock gets left behind. But for every flashy quartz point found, there's a valuable chalcedony nodule or nephrite boulder someone else stepped over. The smarter play is to weigh the oddballs, literally. Use your hand as a first-pass balance. A 3-inch cobble should feel roughly 120–150 grams if it's common rock. If it's over 200 g, you're in dense material territory. Combine that with a scratched window and you're already ahead of most. A dull stone can hold a secret, but only if you know what to feel for. The key isn't color or shine, but the subtle interplay between texture, luster, and form. Many high-value stones begin their journey as opaque, unpolished masses whose outer surface gives only the faintest clues to what's inside. Most walkers miss them because they trust the eye more than the hand. Start with luster. Under natural light, rotate a dry stone slowly. A common rock will usually reflect light in a matte or chalky fashion, but a candidate stone may show an oily sheen, subdued, not glittery, but with a smooth, almost wet look. This is often the first sign of jade, nephrite, or jadeite, chalcedony, or fine-grained opal. It doesn't shine like quartz, it glows softly. That luster is a fingerprint, adamantine or vitreous for some gems, waxy for others. Then there's the texture under your thumb. Silica-based stones like agate or jasper have a fine, almost ceramic smoothness, slightly slick like porcelain. Jadeite often feels greasy or soapy, a result of its interlocking fibrous crystals. When a stone lacks visible grains or cleavage lines and feels unusually smooth, it's worth a second look. Field veterans often test this blind, eyes closed, just fingers on the surface. A quality candidate can be felt before it's ever seen. Now examine habit, the overall shape and pattern. Nodular or botryoidal forms, think grape-like bumps, are common in agate, chalcedony, and some opals. These indicate a slow deposition from silica-rich fluids, often in volcanic zones. If you see rounded, blistered forms, especially with partial banding or concentric zones, you're likely in valuable territory. But beware of one major trap: vitreous simulants like bottle glass. They often have a high luster and can look similar to opal or quartz at a glance. Here, edge behavior matters. Real minerals typically break conchoidally but irregularly, smooth, curved surfaces but not razor-sharp. Glass, by contrast, fractures with unnaturally sharp, clean edges and a more uniform look. If in doubt, scratch it gently on CC sandpaper Mohs ~9. If it powders easily, it's probably glass. Texture clues become more powerful when combined. A dense stone that feels slick, shows oily luster, and breaks with a curved surface should never be tossed aside. Even without color, that's a triple signal. Especially in known gem terrains. These are the exact cobbles cut open to reveal bright green nephrite, deep red jasper, or translucent chalcedony with plume or moss inclusions. It's not just the stone, it's where it lies. Some of the costliest oversights in gem hunting happen not from misidentifying a rock, but from misreading the ground itself. Many promising sites are passed over simply because they don't match the stereotypical image of a gem zone. The truth is, high potential stones often accumulate in terrain that looks boring, disturbed, or even recently man-made. For example, people frequently search upstream in flashy, fast-moving water, assuming that's where the action is. But in gem-bearing regions, value often settles downstream in quiet eddies, old meander scars, or abandoned channels. This is where heavy stones, like jadeite, garnet, or diamond indicator minerals, are most likely to concentrate. Fast water may expose bedrock, but it rarely holds what a gentle bend collects. Another common mistake is ignoring reworked gravel from road cuts, quarries, or construction zones. Many such areas slice straight through old paleo channels, serpentinized zones, or volcanic ejecta fields, exactly the formations known for hosting valuable stones. A dump pile behind a road grader in Northern California once revealed high-grade nephrite that had been unknowingly bulldozed from a serpentine seam. The same mistake has occurred in Australia with boulder opal and in Tanzania with river garnet. Collectors also often dismiss dry creek beds, assuming that water must be flowing for gems to travel. In fact, dry washes in arid regions, especially those cutting across volcanic or ultramafic terrain, can be rich sources of opal, spinel, and even alluvial sapphire. These channels only flow during flash floods, but their load is sorted and dropped with every storm. If the walls show signs of cemented gravels or hematitic crusts, dig a test pit. What's been hiding beneath may surprise you. Slopes are another underutilized feature. While gravity can scatter surface stones, mid-slope benches in mineralized terrain can trap material from upslope pipes or dikes. A rounded green cobble halfway down a serpentine hillside might be the only surface clue to a buried nephrite source. The essential correction is this: don't chase beauty, chase logic. Ask where dense material would end up if it had traveled. Follow the terrain backward from catch points, low-energy zones where water or wind slows, and where you might test sample with far less digging. A single stone, no matter how dense or glassy, means little without the right geological context. It's the surrounding material, the sand, the gravels, the matrix rocks, that tells you whether what you're holding is an isolated fluke or the front edge of something richer. The best collectors know this. Every stone is a clue, but the terrain is the real map. Let's take serpentinized zones as a case study. These ultramafic terrains, rich in magnesium silicate minerals, are the primary host for nephrite jade. You're not looking for green boulders at first. You're looking for veined serpentinite, a greasy-feeling rock often weathered brown or tan on the surface. Look closer, and you'll see its microfractures, sometimes laced with actinolite or tremolite, the fibrous precursors of nephrite. Spotting this host rock means you're in the right place to start checking cobbles for green cores. Even before you find jade, the surrounding indicators point the way. Similarly, in areas with known diamond potential, like parts of Central Africa, Siberia, or the Canadian Shield, kimberlite pipes rarely look dramatic. They may be weathered into clay-rich depressions or slight rises in farmland. But if your pan begins to show chromite, ilmenite, or tiny pyrope garnets, deep red or purple grains about 0.51, you've likely found indicator minerals from the erosion of a nearby pipe. None of these are valuable themselves, but they're your best advance warning that you're near a source that could produce industrial or even gem-grade diamonds. In volcanic zones, context also tells you when to start probing for opal. Rhyolite and tuff formations, particularly where acidic groundwater once percolated, often yield common or precious opal in seams, nodules, or brecciated pockets. If the host rock crumbles easily and shows slight banding, with pink, cream, or gray tones, you may be walking over a shallow opal field. The presence of ironstone or manganese staining further increases the odds. These metals often accompany the geochemistry required for opal formation. What unites these examples is one thing: you're not looking for finished gems. You're building a chain of signs, minerals, habits, host rocks that together tell a story. A lonely green pebble in quartzite terrain might be just a rock, but that same pebble in an actinolite-streaked wash within a mapped ultramafic zone, that's a sample worth cutting. Context also helps you rule out fakes. Finding translucent quartz in basalt flows makes sense. Finding the same in limestone terrain might signal a misplacement or an imported piece. Knowing what should be there protects you from chasing ghosts. If you ever crack a stone open, nature may have already flagged its potential through the company it keeps. Accessory minerals, those small, often overlooked grains and flecks, can be the most reliable field indicators that a valuable gem might be nearby. They're not gems themselves, but their presence in gravels or weathered rock points to geochemical conditions that foster gem formation. Learning to spot them is like learning a new alphabet. Once you know the letters, you can read the terrain. Begin with magnet-friendly suspects. Chromite, ilmenite, and magnetite are dense, often black or metallic minerals that appear in placer concentrates and are easily separated with a simple handheld magnet. If you're sampling gravels with a 20 sieve /0, 85 mesh, and running a magnet through the fines, a strong pull on black grains is an immediate signal to pause. These minerals are especially important in diamond prospecting. Kimberlite pipes tend to weather out with these heavies scattered across downstream points, often miles from the source. Their specific gravities, chromite /455, 1 ilmenite /4 make them ideal for panning concentration as well. Pyrope garnet is another heavy clue. These deep red to purplish grains, usually 0.5 to 2 in size, are highly resistant to weathering and often found in diamondiferous terrains. While pyrope itself isn't valuable, its chemistry, rich in magnesium and chromium, reflects the ultra-high pressure environments diamonds form in. Finding it in quantity in a pan concentrate, especially alongside chromite, should put you on alert. In jade-bearing zones, look for actinolite and tremolite. These fibrous green to white minerals often appear as hair-like inclusions or streaks in host rock, and can even coat pebbles with a thin fuzz of crystal needles. On their own, they're low value, but they often form the matrix from which nephrite emerges. In other words, when you start seeing actinolite, you're getting warm. Volcanic gem fields offer different signals. Manganese oxides, black dendritic patterns or coatings on rock surfaces, frequently accompany opal and rhyolite zones. They're not magnetic, but they're diagnostic of the water-mineral interaction that forms silica deposits. Fire opal fields in Mexico and the US often show these exact coatings near hot spring deposits. If you see that in light-colored, porous rhyolite, start checking cavities and nodules for opaline fill. To separate serious sites from distractions, use these accessory minerals as a first-pass grid. Sample across multiple points with a consistent sieve and pan technique, and record presence or absence. If you find concentrations of 3 or more key indicators in one zone, you've likely identified an upstream source zone worth systematic searching or trenching. When time is short and the terrain wide, simple tools can save you from wasting hours on worthless stones. In the field, 2 of the most powerful early tests are the magnet sweep and the scratch test, and both can be done in seconds. These aren't final answers, but they quickly sort the ordinary from the anomalous, and sometimes they're all you need to spot a sleeper. Let's start with magnets. A small neodymium magnet on a telescopic wand weighs almost nothing and pays for itself in minutes. Run it gently across a pan of concentrates or a dry scoop of sieved material. The telltale pull of magnetite, ilmenite, or chromite gives you an immediate yes zone, especially important when working gravels downstream of a known pipe or serpentine outcrop. These minerals often precede jade, garnet, or even diamond-grade kimberlite material. Note that ilmenite may respond weakly, so watch for grains that try to jump but fall short. That nuance can separate filler minerals from true indicator signals. Then there's the scratch test. A piece of silicon carbide (CC) sandpaper, rated around Mohs 9, is all you need. Drag a clean section of the stone across it and observe the streak. If it leaves a heavy powder or flakes easily, it's softer than quartz, likely a weathered volcanic rock or serpentinite without gem content. But if it resists strongly, leaves little residue, or visibly scores the CC paper, you're dealing with something in the upper 7-9 Mohs range. Quartz, jadeite, corundum, or even diamond simulants. Here, resistance equals promise. Beware of overconfidence. Glass, especially in the form of tumbled bottle shards or slag, can mimic these results. It may resist scratching and pass the luster test, but it usually lacks heft, responds weakly to magnets if at all, and often exhibits perfect conchoidal fracture with razor-sharp edges, too perfect for natural material. Combined logic is key. If your candidate is hard and heavy and magnet-associated, the odds shift rapidly in your favor. You can also scratch test suspected garnets or zircon grains from concentrate. A true pyrope or almandine garnet will visibly etch quartz, Mohs 7, and show subhedral to dodecahedral crystal forms. Zircon, on the other hand, will scratch quartz but often exhibits higher luster and a brownish tinge. It's also slightly radioactive, a trait not worth field testing, but important to note when handling bulk concentrates. Keep your scratch tests consistent. Always test on a fresh face or chipped window. Weathered surfaces can mislead, especially on jadeite, which may seem dull until you expose the interior. And don't rely on just one tool. In isolation, scratch and magnet tests only tell part of the story, but together, they reveal patterns. Thousands of valuable stones are discarded each year because they look too much like glass. Ironically, the very trait that triggers skepticism in collectors, translucence with a glossy finish, is often the clearest early signal of gem potential. Chalcedony, opal, jadeite, and even cryptocrystalline quartz all share this trait, a deceptively smooth, glassy, or waxy appearance that many mistake for slag, bottle glass, or quartzite. Knowing how to tell them apart is one of the most valuable skills in the field. Start with luster and translucency. Real gem materials rarely shine like clean window glass. Instead, they exhibit a muted, almost internal glow, what lapidaries call subvitreous or waxy. Hold the stone against the light. If it allows light to pass but diffuses it heavily, like frosted glass or bathroom tile, it may be chalcedony, agate, or high-grade opal. Glass, by contrast, is often more transparent or has unnatural clarity in fragments. Next, examine how it breaks. True gemstone material typically exhibits a conchoidal fracture, but not as perfect or sharp as man-made glass. Chalcedony and opal break in broad, curved surfaces with slight irregularities, like ripples frozen in wax. Glass tends to cleave cleaner, with razor edges and homogeneous sheen. Test this by making a small controlled chip with a hammer and chisel. If the break reveals a milky interior and irregular wave patterns, you likely have natural silica. Color is another critical clue, but not in the way most think. Valuable glassy stones are often white, pale blue, light gray, or completely colorless. These are the shades most people ignore, assuming they're too plain to matter. But in the field, these subtle tones often correspond with high silica content and cryptocrystalline structure. Translucent white nodules in rhyolite terrain may be common opal, especially if manganese or iron stains are nearby. Slightly blue stones in basaltic zones can indicate silica replacement of vesicles, another opal formation path. One of the easiest field mistakes is dismissing nodules with surface crazing, fine cracks, or a chalky rind. In reality, that may be the dehydration crust of precious opal. The core could still be stable, vibrant material worth hundreds per kilo. Similarly, weathered agate often forms a powdery shell from oxidized outer layers, concealing vivid color bands just millimeters below. To sort glassy candidates quickly, run a density check by feel. True opal and chalcedony are heavier than glass Sg2, 022, and closer to quartz Sg2, 65. Even without a scale, a practiced hand can feel the difference. A 3-inch nodule that feels light is likely slag. One that feels dense and compact may justify a water displacement test to confirm specific gravity, especially if other indicators match. And don't forget to combine clues. A translucent nodule with waxy luster, non-sharp breakage, slight heft, and surface banding or dendritic inclusions. That's not trash. That's cuttable material, possibly even gem grade, with value depending on pattern, clarity, and size. To the untrained eye, a pan of gravel is just a mess of mud and rocks. But to a practiced collector, it's a diagnostic test that can shrink hours of searching into a few decisive minutes. By running a proper sieve and pan setup, even with basic gear, you can rapidly isolate heavies, flag promising accessory minerals, and zero in on stones worth cutting or testing further. This is where overlooked materials reveal their density, and density never lies. Start with the sieve. A stack of 20-0, 85 and 40-0, 425 screens is enough for most fieldwork. Use the 20 to remove larger cobbles and organics, then the 40 to narrow down to sand-sized and smaller grains. What you're after is the mid-range concentrate, what stays on the 40 but drops through the 20. This layer holds most indicator minerals, pyrope garnets, chromite, ilmenite, and zircons, as well as small gem fragments. The finest material, what falls through the 40, is mostly silt and clay, and can usually be discarded unless you're after micron gold or tin. Next comes the pan. Use a standard black plastic gold pan or a shallow steel batte. The principle is simple. Agitate the material in water, let gravity do the sorting, and gradually wash away the lighter fractions. What remains in the bottom, called the heavies, is where the story begins. A dark streak of magnetic grains, flecks of deep red garnet, or even opaque blue-green pebbles tucked at the edge of the pan's swirl can all signal a gem source nearby. Interpreting this concentrate is part science, part art. Magnetite and ilmenite form the bulk of black sands in many regions, but look closely for grains that are submetallic or reflect light with a bronzy or purplish hue. These may be chromite or even spinel. Garnets show up as rounded grains with a subtle sparkle, while zircons are typically angular and colorless to yellowish, sometimes with high relief under a loupe. Crucially, what doesn't stay in the pan is just as important. If your target stones float off early or roll too easily, they're likely too low in specific gravity to hold cutting value. Chalcedony, jade, and opal aren't especially dense, 2, 5-3, 0, but they often appear as rounded pebbles in the +20 fraction, too large to pan properly, but worth testing if they exhibit the right surface traits. Sorting should be methodical. Document each site, noting the number and type of heavies recovered per pan. If you're seeing consistent garnet and ilmenite across multiple samples in one drainage, you may be closing in on a source, especially if the grain size increases upstream. A sudden absence can signal you've moved past the productive zone or crossed a fault. Some of the best recoveries happen in places others ignore: dry tailings, flood-scoured bends, or even the undersides of large boulders. In drought years, long-buried concentrates become accessible. Use a flat shovel and break apart compacted gravels with a pick or mattock before running your sieve. Often the best indicators hide just below a few inches of overburden. The closer you get to a promising field find, the more dangerous false positives become. Few things waste more time or lead to more disappointment than chasing high-luster, high-hardness stones that seem like wins but fail under scrutiny. Among these, moissanite and zircon are the most notorious. They sparkle like diamonds, resist scratches like corundum, and even mimic the heft of true gems. But without the right field tests, they'll fool even experienced hands. Start with zircon. It's a common accessory mineral in igneous rocks and often appears in pan concentrates as angular grains with an adamantine luster. In some terrains, particularly those rich in granites or pegmatites, it's everywhere. But its clarity and shine make it deceptively attractive. It registers about 6, 5, 7, 5 on the Mohs scale, sometimes more depending on impurities, and its heavy, specific gravity hovers around 4.6. This heft makes it linger in pans and sieves, giving it the feel of a keeper. Yet the giveaway is its brittleness. A controlled tap test, one light strike with a hammer on a protected surface, will often shatter zircon along cleavage planes. Genuine diamond rough or jadeite will resist this kind of impact or break more cohesively. Zircon also tends to fluoresce under shortwave UV, sometimes yellow to orange, a clue but not definitive. Moissanite is even trickier. Synthetic versions flood the market and sometimes appear in tailings, especially near old lapidary or industrial discard sites. It's harder than corundum, 9.25 on the Mohs scale, and conducts electricity, unlike diamond. That's your ACE test. A handheld conductivity meter, if available, instantly separates moissanite from diamond or sapphire. In the field, you can also look for doubling under magnification. Moissanite is doubly refractive. A loop will show ghosted edges or facet doubling not seen in diamonds or single refractive stones. Moissanite's brilliance can be misleading. It reflects more fire than diamond, often to a fault. If a stone in your concentrate seems too sparkly, especially under direct sun, be skeptical. Real diamond rough and less weathered is less ostentatious, often appearing greasy or dull until properly cleaned and faceted. A second field test involves thermal conductivity. Pocket diamond testers are cheap and reliable in dry conditions. Moissanite typically sets off a false diamond reading due to its similar thermal profile, but advanced testers with dual mode, thermal and electrical, eliminate that confusion. If you only have basic gear, use redundancy. Visual ghosting, scratch resistance, and weight SG estimate by hand or displacement. Field-wise, context also helps filter the suspects. If you're pulling brilliant grains from a known granite zone with high accessory zircon, odds are it's zircon. If you're in alluvial deposits downstream from lamprite or kimberlite terrain and also seeing chromite or pyrope garnet, you may have the real thing, but proceed with caution. Size, context, and behavior must all align before assuming value. Don't forget cost logic. Moissanite and zircon are both used in industrial processes and low-end jewelry. If you're finding unusually clean, large grains in odd places, like roadside fill or tailings, it may be discards, not naturals. Real diamond rough is rarely concentrated in such accessible zones without strong indicator support. Sometimes it's the stone you almost leave behind that holds the real reward. In gem hunting, the breakthrough often comes not from a dazzling surface, but from a fracture line, an accidental chip or deliberate strike that reveals what years of weathering have hidden. This is the moment every field collector waits for, when an unremarkable cobble cracks clean and the interior flashes something the outside never promised. Picture a smooth, dense, green-gray boulder found halfway down a dry slope. It's heavier than average, non-magnetic, with a dull, waxy luster. Too plain to spark excitement, too hefty to dismiss outright. After a scratch test shows strong resistance and a conchoidal chip, it's tapped along a natural seam. The break is immediate and silent. Inside, there's a uniform pale green translucence that catches the light, not with sparkle but with depth. It's not glass, it's not quartz, it's nephrite. That smooth, fibrous sheen, the so-called greasy polish, is unmistakable once seen in the field. It doesn't glint, it glows. And unlike serpentine, which it often resembles on the outside, true nephrite feels more cohesive, less brittle and denser in the hand. On break, it doesn't fracture grain by grain, but yields in smooth arcs with almost no dust. That behavior alone puts it in a new class. In another case, a pale brown nodule from a rhyolitic slope cracks under hammer pressure. The outer shell crumbles, revealing a core of jelly-like opal, pale blue to white, with hints of play of color along its inner surface. It had shown no hints, no crazing, no color from the rind. But the internal structure, the way light diffuses, the slightly oily surface when damp, immediately raises its profile. A water dip test confirms it. The luster tightens, the translucence increases, and fine rainbow fire emerges at the edges. Precious opal, uncut and unpromising just hours ago. These moments don't happen by luck. They come from pattern recognition and repeated testing. If you've identified indicator minerals, sieved concentrates with heavy accessory profiles, and cross-checked luster and heft, the odds of finding a cuttable core increase exponentially. But even then, the final proof often comes from a break. That's why seasoned field collectors carry chisels, protective goggles, and a commitment to sampling methodically, without rushing to judgment from the surface. What you do after the crack matters just as much. Take photos, document GPS coordinates, and compare broken faces to known samples. If translucence, color uniformity, and texture suggest value, protect the remaining piece. Don't oversample. Transport carefully. Many valuable cores lose hundreds in value from a second unnecessary hit. Yet a single find isn't a pattern. One stone with a hidden core could be a fluke, or it could be the lead edge of a deeper concentration. That's when emotion has to give way to process. You need to verify, not just the stone, but the repeatability of the location. One stunning core doesn't make a deposit. No matter how vivid the jade, how brilliant the opal, or how glassy the chalcedony, a single piece is just a sample. The only way to move from curiosity to credibility is through verification, building a repeatable workflow that confirms not just the stone's identity, but its pattern of occurrence in the field. This is where the collector becomes an investigator. Start with the basics: grid and record. Once you've recovered a promising specimen, return to the exact location and establish a simple grid, 10-meter intervals in cardinal directions, marked with flagging tape or GPS waypoints. At each point, take consistent samples: a few liters of surface gravel, a slice of subsoil if applicable, and any cobbles with the same feel or visual characteristics as the original find. The goal is to map density and distribution, not just chase beauty. Within each sample area, run the same sieve and pan workflow as before: hash 20 and 40 mesh screens, magnetic pass, scratch triage, and water-based separation. Record the results: number and type of heavies, color and texture of potential gem nodules, and any accessory minerals present. Consistency is everything. If garnets, chromite, or actinolite appear in 3 or more adjacent samples, you're likely tracking a legitimate horizon. Then escalate: subsurface probes. Use a handheld auger or shallow trench to expose material below the weathered layer, often where richer deposits hide. In ultramafic terrain, nephrite-bearing seams may lie just beneath oxidized serpentinite. In volcanic zones, opalized cavities may form in soft tuff or breccia, invisible from the surface. Document each probe: depth, host rock, and any mineralization observed. Next comes sample repeatability. Collect 3 to 5 suspected gem materials from different grid points, ideally with similar weight, texture, and surface traits. Test them side by side: break surfaces, water dip, loop inspection. If the internal characteristics match, translucence, fracture pattern, luster, you're building a case for a coherent occurrence, not just scattered float. At this point, resist the urge to send your best sample to a lab. Instead, isolate the most representative, not most attractive piece. Labs don't need beauty, they need typicality. Include field notes, location context, and mineral associations. A reputable gem lab will test for refractive index, SG, UV response, and microstructure, confirming if you have nephrite versus serpentine, opal vs silica glass, or even a genuine jadeite cluster. If the lab confirms gem potential, return to your grid and expand the perimeter. Look for the geological controls: faults, lithological boundaries, paleo channels. These often confine or direct gem deposition and help narrow down target zones. Use each verified stone to triangulate the most probable upstream or in situ source. Finally, record everything digitally: photos, GPS data, sieve results, and test outcomes. If you ever sell, partner, or seek a claim, this log becomes your foundation. Gem discoveries aren't just about beauty, they're about proof. Knowing what to look for in a stone is only half the equation. The other half, perhaps the more important half, is knowing where to look. Gem-bearing terrain doesn't advertise itself with bright colors or lush scenery. More often, the richest sources lie in rugged, overlooked, or geologically quiet regions that mask the intense processes occurring underground. Each gem type has its own preferred geologic neighborhood. Recognizing these profiles lets collectors target the right places and skip the dead ground. For jadeite, The terrain of choice is subduction-related metamorphic belts, zones where ancient ocean crust was pushed beneath continental plates. These regions host high-pressure, low-temperature metamorphism that produces jadeite-bearing rocks. You'll find such profiles in northern Myanmar, Guatemala's Motagua Valley, and parts of Japan. Field indicators include serpentinite masses, rhodingite dikes, and quartzalbite veining, all common companions to jadeite. The landscape may look subdued, weathered hills, dry creek beds, but if you spot green cobbles with waxy luster near a serpentinite cliff, you're in play. Nephrite jade prefers ultramafic terrains, ancient seafloor or mantle rocks brought to the surface through tectonic uplift. British Columbia, Siberia, and parts of western China host the best-known deposits. The terrain often features brown or greenish slopes littered with serpentine boulders. Pay attention to talus slopes and glacial outwash zones, where boulders may be exposed or rolled far from their origin. The presence of actinolite or tremolite veins in host rock signals proximity. Diamond terrain is tied to kimberlite and lamprite pipes, ancient volcanic conduits that erupted rapidly from the mantle. These are rare, but unmistakable when properly mapped. The pipes themselves are often weathered into shallow depressions filled with clay-rich soil. The surrounding terrain may appear flat or featureless, especially in regions like Botswana, Siberia, or northern Canada. But pan the local streams, and you may find chromite, pyrope garnet, or ilmenite, key indicators eroded from a hidden pipe. For opal, volcanic terrain is essential, especially rhyolite flows and tough beds altered by acidic groundwater. Look for regions with known hot spring activity, past or present. Australia's Lightning Ridge and Coober Pedy, Mexico's Magdalena District, and Ethiopia's Wollo Province all fit this bill. Surface terrain is usually dry, dusty, and dotted with ironstone boulders or bleached caliche layers. Shallow digging near faulted or brecciated zones often reveals opaline nodules. Watch for manganese dendrites or flow banding, both signs of silica movement. Chalcedony, agate, and jasper form in a wider range of environments, but concentrate where silica-rich fluids infiltrated voids, often in basalts, welded tuffs, or fault breccias. Terrain may include dry washes, broken mesas, and basalt-capped plateaus. The American Southwest is rich in such terrain, as is Madagascar and southern Brazil. Nodular habit, banded structure, and high gloss often appear in float material even far from the source. Understanding the interplay between rock type, hydrology, and tectonics helps narrow the field even more. For instance, a basalt flow overlying a fossilized hot spring site might yield both opal and agate. A glacial moraine cutting through ultramafic rocks may scatter nephrite across kilometers. Terrain logic lets you anticipate concentrations before you dig. Field success means little if the ground underfoot gives way, or if your best find is confiscated for trespassing. In gem hunting, safety and legality aren't bureaucratic afterthoughts, they're core competencies. Some of the most promising terrain also presents the greatest physical risks and strictest access controls. Understanding how to navigate both is essential for any serious collector. Start with the physical. Slopes and flood zones are the two most underestimated dangers. In ultramafic terrain, weathered serpentinite decomposes into slick, unstable clay. A dry hillside can turn into a slide zone with the first rain. Never dig into unsupported slopes and avoid trenching at the toe of a hill without testing slope stability. Where possible, dig from the top down or from a lateral bench, not into a vertical face. Flood risk is just as real. Dry washes and streambeds in arid zones can surge without warning from upstream rainfall miles away. When working in desert opal or agate zones, always check the weather upstream, even if your sky is clear. Avoid digging in low cuts or arroyos unless you're confident in the drainage window and can exit quickly. Look for high ground escape routes before you start sampling. Then there's hazardous rock. In serpentinite and volcanic terrain, you may encounter asbestos fibers, especially chrysotile, arsenic traces, or heavy metal contamination in soils. Wear gloves, avoid inhaling dust, and carry a mask if you're working with dry, friable rock. Don't break or crush material in confined spaces without ventilation. In some zones, water runoff can carry contaminants downstream. Avoid drinking untreated water near old mines or mineralized zones. Next is access control, a legal and ethical minefield if you're not prepared. Not all promising terrain is public land. Many known gem areas lie within national parks, reserves, or privately held mining leases. Collecting in these areas without explicit permission can result in heavy fines or confiscation of gear and material. Always check jurisdiction. In the US, use BLM and Forest Service maps. In Canada, consult provincial tenure registries. In Australia, state departments manage mineral rights distinctly by region. Where allowed, casual collecting is often limited to hand tools, surface sampling, and non-commercial quantities. Anything beyond, digging with heavy equipment, collecting large volumes, or removing host rock, may require a prospecting license or exploration permit. These are often inexpensive and provide legal cover for sampling, recording finds, and staking claims if a deposit proves viable. Ethical sourcing also matters, especially in areas where land use overlaps with indigenous or cultural significance. In parts of British Columbia, Guatemala, and Myanmar, jade fields cross traditional territories. Even if access is not legally restricted, responsible collectors avoid disturbing sacred sites or entering zones flagged by local communities. Building local knowledge and seeking guidance can open doors that GPS coordinates never will. Finally, plan for emergency response. Remote collecting often means no cell signal, rough terrain, and few passersby. Bring a personal locator beacon or satellite messenger. Let someone know your route and return time. Carry water, basic first aid, and protective gear for breaking or lifting rock. A promising find is no use if you can't get back out, or if you get hurt bringing it up. With safety and access squared away, you're in a position to continue serious recovery. But even with a verified zone and permission to collect, the question remains: when should you pay for full lab assays, and when is field verification enough? Next, we build a strategy for smart testing, balancing cost, confidence, and when to pull the trigger on certification.